Hello, and thank you for opening this YouTube video. It is a part of the Nearly Carbon Neutral Conference 2022, and I'm very glad to be giving it. So I'll be talking about constructing proper affine actions via higher strip deformations, which is a construction that I introduced in my recent paper that went up on the archive this summer. So let's first talk about some motivating questions for why we would like to know more about affine actions. So it's a classical theorem of Bieberbach's that says that if gamma is a group of Euclidean isometries acting properly discontinuously and co-compactly on Euclidean space, then gamma is virtually free abelian. What this means topologically is that if I have a compact Euclidean manifold or orbifold, it is finite covered by a Euclidean torus. So this is a very strong structure theorem for Euclidean manifolds, and there's a conjecture called the Auslander conjecture, which relaxes some of the assumptions of Bieberbach's theorem, namely it removes the assumption of the action being by isometries. So more precisely, it says that if a group acts properly discontinuously and co-compactly by affine transformations on affine space, then gamma is virtually solvable. This conjecture is known for manifolds up to dimension 6 and is unknown for higher dimensions. Shortly after this conjecture was first proposed, Milner asked if all of the conditions of the conjecture were in fact required, namely, is the co-compactness required? So can we say anything about the fundamental group of an affine manifold that is not necessarily a compact manifold? And Margulis basically answered, no, we can't really say much about the fundamental group of such a manifold by constructing a free group that acts by affine transformations on three-dimensional space properly and discontinuously, but not co-compactly. And manifolds that we would get as quotients of these kinds of actions are called Margulis spacetimes. So there are many people who have worked on this problem of describing and classifying three-dimensional Margulis spacetimes, and some that should be mentioned here in addition to Margulis are Drum, Goldman, Mass, Charette, and Danziger, Garito, and Castle. In fact, the theory of three-dimensional Margulis spacetimes is well understood. There's a theorem by Danziger, Garito, and Castle that describes exactly how we can deform a given linear part, a given free group, to act properly discontinuously on affine 3 space. So given any discrete free group in SO21, they can construct all the proper affine deformations of that linear part, so by adding some translational parts to all the elements, and that set is naturally parametrized by the arc complex on a non-compact hyperbolic surface. In higher dimensions, the situation of what's going on with affine actions on higher dimensional affine spaces is less well understood, but a lot of work has been done on this question by, say, Abus, Margulis, Soifer, as well as Smilga. And what I'll be talking about today is a new family of proper affine actions on affine n space for n3 mod 4. And the main tool that I am using is the Margulis invariant, which was first introduced by Margulis in the 80s when he first constructed his examples of Margulis spacetimes. In order to talk about the Margulis invariant, let's first talk a little bit about the dynamics of elements in SO21. If we take a loxodromic element in SO21, so this is a matrix, a linear transformation with 3 distinct real eigenvalues. It turns out it has to have 1 as an eigenvalue, and its the corresponding eigenvector is called the neutral vector. We can consistently orient it and norm it because it is always a space-like vector. And we will be denoting it throughout by x0 of gamma. So if we have a subgroup in SO2-1 consisting of purely loxodromic elements and a gamma cocycle, which just means that the cocycle condition is satisfied, then we can define the Nord-Margulis invariant. It is a class function on gamma, linear in U, invariant up to conjugation, defined by using the 2-1 bilinear form that SO2-1 fixes. And it sends every element of the group into the inner product of the neutral vector of that element with the translational part of that element. So these are both vectors in R3. And we divide it out by the translation length of gamma as a hyperbolic isometry. When Margulis first introduced this invariant, he also proved Margulis's opposite sign lemma, which says that if we have a group acting properly discontinuously on affine 3 space, then either all the Margulis invariants are positive or they're all negative. In fact, it's not that difficult to see that if the Margulis invariant takes the value 0, that element on which it takes the value 0 has to have a fixed point. So right now, this is just a story in 3 dimensions, but elements in SO2n to n-1, so almost split signature, have very similar dynamics, and we can make sense of all of this for loxodromic elements in SO2n to n-1 as well. Now, you might note that Margulis's opposite sign lemma is not an if and only if statement, and the reverse direction was proved later by Goldman, Laborie, and Margulis, and it also works for Fuchsian groups inside of SO2n to n-1. So these are groups coming from the irreducible representation of SO2-1 on 4n-1 dimensional space. And it states that a group acts properly discontinuously on affine 4n-1 space exactly when all of its Margulis invariants are bounded away from 0 and are either all positive or all negative. And it uses geodesic currents to prove this statement. Now, this is a talk in the Anossov representation section of the conference, so I would be remiss not to mention that there is a generalization of the Goldman, Laborie, and Margulis theorem to affine Anossov representations, where we can replace the Fuchsian linear part in the Goldman, Laborie, and Margulis theorem with any Anossov linear part inside of SO2n to n-1, and we can still make sense of what the Margulis invariant means in that case, and that was developed and proved by Gaussian tribe. So this invariant tells us exactly when an action is proper. We only need to compute the invariant for all the elements, in order to say definitely whether or not an action is proper. And this is the tool that I will use to show that the family of actions I construct is going to be proper. So let me describe what a higher strip deformation is. And let me first mention that this is heavily based on work by Dancy, Gargarito, and Castle, where they explore strip deformations and infinitesimal strip deformations, which work for constructing affine actions in dimension 3. Here we are going to try to construct affine actions in dimension 4n-1 for any n. So we will start off with a convex co-compact, non-compact hyperbolic surface S, whose fundamental group is a free group. And the hyperbolic structure on S allows us to identify its fundamental group with a subgroup of SO21. And then we use the irreducible representation into SO2n 2n minus 1 and get a Fuchsian free group inside of SO2n and 2n minus 1. So what we would like to do is construct a cocycle of this free group inside of SO2n 2n minus 1. So what we need to do is associate a translation part to each element gamma of our group. So let us fix something that we call a strip system. It consists of a bunch of properly embedded arcs. Here we have an arc A drawn in light purple in the picture, and on each arc a point, and at each point a direction or like an angle. And now I will describe a procedure to turn this information into a cocycle for the fundamental group gamma of this surface. So I think it's easiest to just do it by example. We have to lift our strip system to the universal cover H2 of our surface S and pick a base point. So I am denoting the base point here by x0. Then we translate the point x0 by our given element gamma and get gamma dot x0, and there is some oriented path between these 2 points. And it crosses some number of lifts of the arc A, and each time it crosses, we are going to add something to the translational part of our element gamma. And the thing we're going to add is determined by this point and this angle on our arc. Namely, we will consider a hyperbolic translation eta whose axis of translation goes through the point at the specified angle. So in my picture down here, I have eta 1 going through the lift of the point on the arc A1 at a specified angle, and eta 2 going through the lift of the point on A2 at the specified angle. And what I do is I take the neutral vectors of the images of all of these etas and add them together each time the path corresponding to gamma crosses an arc. So in the case drawn here, I would add the neutral vector of eta 1, so a vector in R for n minus 1, and the same thing for eta 2. Remember, this x0 denotes the eigenvalue 1 eigenvector of the loxodromic element sigma of eta 1 or sigma of eta 2. So why this is useful is because it turns out that the Margulis invariant of a deformation defined in such a way is fairly tractable to compute. As long as I choose an equivariant family of vectors associated to each of the arcs, I could do this much more generally, but it would be computationally harder. So we're going to make the computation in the Fuchsian case, and in the case where the translations we're adding are coming from hyperbolic geometry in this very simple way. So how would I go about computing the Margulis invariant? Well, let me focus on just one intersection of gamma with an arc in my strip system. So I can always translate my picture around, conjugate if I have to look something like this. So in this picture, this point here is the lift of the chosen point on my arc. By eta, we are denoting the hyperbolic translation translating along this geodesic at the specified angle to my arc. and gamma here is the axis of the element gamma. So in order to compute the Margulis invariant, if you remember, I have to compute the inner product of my neutral vector of the linear part with the translational part of that element. But the translational part is just a sum of elements that look like this. So it is enough to just compute the inner product of two vectors coming from this hyperbolic geometry picture. And it turns out that I can write down what this is in terms of the cross ratio of the endpoints of the axes of eta and gamma. In the picture I drew here, the cross ratio is just t, which is where gamma is pointing. And it is a rational function in the cross ratio with one pole. There's always a pole at t equals 1 coming from this division over here, and 2n minus 1 zeros. So we have 2n minus 1 zeros in the pole. They are all real simple zeros. So we have a sign switch at each of them. Oh, and this function extends to the extended real line. We can add infinity, and it's continuous at infinity. And this function takes positive values between 1 and up to infinity, negative values down here, and then it switches sign many times. So what does this mean for our computations, for constructing proper affine actions? If you'll recall, we want all the Margulis invariants of all the elements to be, say, positive in order to guarantee that our action is proper. And in higher dimensions, this is kind of finicky. We could have good intersections and bad intersections. Our gammas could be pointing relative to the etas, either to the blue or to the red regions. So let's just see what happens for some small dimensional examples. Namely, for n equals 1, I just get a very simple function that only has 1, 0, and 1 pole. And in fact, our construction of these higher strip deformations recovers infinitesimal strip deformations from Danziger, Garrito, and Castle. And in Danziger, Garrito, and Castle, it does not matter so much how exactly you pick your arcs and how exactly you put these translational parts on them, which is reflected in this picture. As long as the orientations of eta and gamma match up, we are always going to be hitting a blue region in the space. So in this case, no matter how we choose our etas in some sense, we are going to be getting a positive contribution to the Margulis invariant each time our gamma intersects a given arc. Already for n equals 2, so for affine actions on 7-dimensional space, the situation is more complicated. Our function now has 3 zeros in the pole and switches sign 4 times, like in this manner. So if the angle between eta and gamma can be guaranteed to be steep enough, we know that we're going to end up in the blue region. But if we can't guarantee that, then we could end up in a red region, and we would need to have more control over the geometry of the surface to ensure this does not happen. Or we would want to hope that somehow these positive and negative contributions cancel out. So my result is that we can always construct proper affine actions using this construction, namely if S is a convex co-compact hyperbolic surface that's not compact, but there is always a strip system that determines a cocycle whose action is proper on affine 4n minus 1 space. And in fact, we can say a bit more. We can find a family of these actions that spans an open set in the space of cocycles. Now, knowing what we know about this sign switching behavior of the Margulis invariant, the proof is not that difficult, at least not intuitively. Namely, we can choose our translations, our etas, in such a way that they lie completely outside of the convex core. That means that no matter which closed curve gamma we choose, it is not going to intersect with the translational part at all. So in this picture back here, we are forcing, by choosing translational parts eta to lie outside of the convex core, to always be in the situation where gamma and eta do not intersect. So all of the closed curves are going to be making a pattern like this with the translational parts. And from this picture, you can see that that region of the circle of the boundary of H2 is always blue, no matter what, because all the zeros of this contribution function are negative. And we need to check that this gives us uniform positivity, but adding up all of these contributions ensures that the Margulis invariant of each individual element is positive, and uniformity gives us that the action is proper by the result by Goldman-Abreu Margulis. And I think this is all I wanted to say about this right now. But if you have any further questions, please drop them in the Discord for the conference or come to the office hours. And if you are watching this after all the live events for the conference have already ended, please feel free to shoot me an email. I would love to talk about this some more. And thank you for making it through all the way this video.